Hello and welcome to the 8th and last session of David Auerbach's From Leibniz to Google, 5 Paradigms of Artificial Intelligence. Please, David, take it away.
Hi, welcome back. We have a lot to cover this week, and we have a number of presentations, so I want to just get right started. I want to do this as a fence post approach to the explosion in AI and specifically deep learning in the last 10 to 15 years. So I'm going to begin with a few comments more generally about deep learning. And the basic move in deep learning, which should be apparent from the readings, is that you take these parallel distributed processing approaches and you scale them up massively. You throw huge amounts of processors at the problem and huge amounts of data. And ironically, this is what the symbolic AI people had been asking for as a prerequisite to their own accomplishments. Just wait a little longer, they said, and we'll get over the hump of not having generalized knowledge because we just need more computational resources. And some of them are still saying it. And then suddenly around comes, well, Google in particular, as well as Facebook, with racks and racks of servers that they can throw thousands, if not tens of thousands of CPUs and GPUs at a single distributed task. And sometimes you don't even need that. AlphaGo 0 only needs a few dozen high-performance processors and a few days of training in order to beat every other program in existence and every human, and that's quite remarkable. But that increased amount of processing in combination with some new mechanisms that are geared as much to efficiency as they are to depth, and the Hinton papers discuss this in detail. The point is, much of the scaling up deep learning did was a matter of figuring out algorithms that allowed neural networks to grow in size without growing at a nonlinear rate that would cause connections between nodes to explode out of control as the number of nodes went up. So in that particular regard, AI has really become an engineering problem. How can we just make it bigger? Because making it bigger seems to actually be working. Because ironically, and I suppose frustratingly, to the symbolists, scaling up seems to work for PDP, and to the extent that the size of a network often becomes an indicator for its quality and abilities. And I was going to hope that Nikita could present on the deep learning book right now, but he's not here, so I'm just going to keep going. I think Stefano will probably be, actually maybe we can do it, maybe we can do someone else's presentation right now, maybe.
I could talk about Go, since you just mentioned it now.
Go is going to come later, actually. Okay. Stefano, do you want to go right now, actually, since we're talking about philosophical deep learning? Wait, Stefano's not here either?
I can't see him.
Oh, great. Well, this is how it works. I want to hold off on Go because it's pretty particular. Oh boy. What do we have here? I don't want to do Gary Marcus just yet. Okay, I'm going to keep speaking. All right, so here are two quotes. This is the Krzyzewski paper on page 90. This is speaking to scale. It is notable that our network's performance degrades if a single convolutional layer is removed. For example, removing any of the middle layers results in a loss of about 2% for the top one performance of the network. So the depth really is important if we're achieving our results. And now the deep learning textbook on page 360, convolutional nets were some of the first working deep networks trained with back propagation. It is not entirely clear why convolutional networks succeeded when general back propagation networks were considered to have failed. It may simply be that convolutional networks were more computationally efficient than fully connected networks, so it was easier to run multiple experiments with them and tune their implementation hyperparameters. Larger networks also seem to be easier to train. These are both examples of what might be called retrograde speculation. Instead of AI people speculating on what it might take for a machine to emulate the mind or how much more they need before they can emulate the mind, now they're speculating on how the machine did what it did in the first place. And in both of these cases, there's an almost laissez-faire attitude towards the success, sort of revised functionalism. It's not saying that what's inside the black box doesn't matter, but that it's neither a clear nor an urgent matter why this black box is performing as well as it does, other than, you know, the quantitative metric of it having this many layers. We peek inside and we see more convolutional layers, and that's an indication that the network is better and more mind-like, at least in terms of trying to reach the metrics we desire. I think that as deep learning runs up against its limits, there is going to be more investigation as to exactly why the additional layers cause so much benefit. In some cases, it's clear when the layers show a clear hierarchy and locality of purpose, but honestly, most of the big networks are just too big to decompose in that way. And now there are, with deep learning, there are some new developments in terms of methods, but these are effectively refinements of how to judge the topological spaces that are being created by input vectors, such as better approaches to gradient descent and fitting. I haven't seen anyone really claim that these developments are revolutionary, even though they're very impressive from an engineering point of view. And that, I think, helps give an answer to a significant question, which is, you know, is deep learning actually a new paradigm if the methods being used emerge so directly from the previous paradigm of parallel distributed processing, and many of the central figures involved are either the same as with Geoffrey Hinton, or they're students of Hinton and Rumelhart or other major PDP figures. Unlike the previous transitions we've seen, which all entailed a significant rejection and reorientation of the fundamental philosophical and conceptual underpinnings of the previous paradigm, there's no animosity whatsoever of the deep learning people toward their predecessors. In fact, there's a streak of proud vindication because there's the sense that while, you know, while AI was scrambling in the 90s trying to find anything that worked, and neural networks in particular were somewhat relegated to being a niche topic in computer science, now it's turned out that deep learning neural networks in particular have proven to be better at solving many, many problems, often in a more generalized way than approaches that were once thought more promising. But I would still argue that it is a paradigm change because for several reasons. The first is that the underlying nature of the claims has changed, even if the techniques have not. In the deep learning readings, I hope you all noticed a fairly significant change in the rhetoric and, I guess, and stated goals from the PDP readings. And I wanted to ask if anyone would like to speak to that as to what they noticed in that regard.
I kind of kept noticing that, or in general in the readings, last week I attended a talk by Elena Esposito, the system theorist, sociological person. And I guess this is kind of like something that I notice is that, and you'd find in a lot of like sociological or critical theory papers on the topic, is that it seems as if the idea of like linear causality is losing its kind of like primacy in how we think about like knowledge generation or scientific endeavor. So it's much more, it's not that correlation replaces causation, but it's certainly a much more prominent and like foundational epistemological commitment that seems to be changing at the moment.
I think, yeah, you raise a very good point, which is that you know, these networks are very good at establishing correlations. I mean, that's in large part that's the major thing that they do. They say, okay, well, let's find the point at which the correlations we wish to represent are best captured by, you know, fitting a function or some sort of like dividing line or partition. There's a great book by Judea Pearl called The Book of Why, which I highly recommend. Pearl was I guess one of the, if not the inventor, certainly one of the main inventors of Bayesian belief nets. And he makes the case that causal relationships need to have some sort of primacy in how relationships are constructed, and that this cannot be captured simply through observances of correlation. And the question then becomes, how on earth do you implement these things? How on earth can you get a network to have those notions in a way that is different than correlation? And I think that again, or actually, does anyone else have a comment on the change in orientation that they'd like to observe? Well, I'll say that I think one of the reasons is almost inertial, the achievement of practical successes. That when you see something working, you're inclined to conclude that you've captured enough, and if causation isn't there and you're getting good results, maybe causation isn't required. And just as symbolic AI got some traction by creating actual programs that could do actual things, like playing checkers, being a big one, the triumph of deep learning is in many ways a practical one. We see over and over again in the papers that deep learning beats up various other machine learning approaches or non-machine learning approaches on this or that task. And when it does something like crush all other computer models and humans at Go, that's an undeniable milestone that makes it all the more perplexing that we don't understand why it does it so much better. And because we still don't have our other folks, I am now going to invite our Go specialist, Guillermo, on Go a little early.
That's fine.
Thanks, Guillermo.
Just give me a minute to open the tab.
Who here, does anyone here play Go? Guillermo, do you play Go?
No, I have never played Go, and I've read the rules and I know the very basic principles of it, but I'm no specialist at all, quite far from it actually. Do you play?
For all practical purposes, no. I'm at the point where saying I play Go would just result in me being embarrassed if I were to play a game. I think that's probably the best way to put it.
It's also funny because the team that devised AlphaGo, I remember watching the documentary when they're in the last game and they think that the machine is not playing accurately. They also recognize, we actually don't know a lot about Go, but they ended up creating the best player ever of Go, but even they themselves, they didn't really know the game very well.
Yeah.
You see my screen?
I can see you've got a very slow download going.
Oh, that's true. Okay, so yeah. So I'm just gonna begin by explaining the game of Go and its basic rules for everyone to get a sense of the game and myself too. So this is the board of Go, and Go is an abstract strategy board game for 2 players in which the aim is to surround more territory than the opponent. It is considered to be the pinnacle of board games. The playing pieces are called stones. One player uses the white stones and the other black. The players take turns placing the stones on the vacant intersections of a board. Go pits 2 players against each other across a 19 by 19 grid. The players take turns putting stones at intersections, black versus white, trying to enclose territory or wall off swaths of their opponent's color. People say chess is a metaphor for war, but it's really more a metaphor for a single battle. In comparison, Go is considered to be like a global battle space or even geopolitics due to its ripple effects. A move in one corner of the grid can ripple everywhere else. Advantage ebbs and flows. In a game of chess, a player typically has about 35 possible moves to choose from in a given turn. In Go, the number is closer to 200. A standard chessboard is played on 8x8 grid of lines. The standard Go board has a 19x19 grid of lines. Chess already represents a vast number of possibilities, even more than the number of atoms in our observable universe. But while chess has 10 to the power of 120 possible board configurations, the game of Go has 10 to the power of 174, which represents 1,000,000 trillion more configurations in chess. Unlike chess, where there are good and bad moves that can be determined with strategic forethought through likelihood in a winner-takes-all kind of game, Go's principles are more based on intuition, qualitative measures, and judgment. Once placed on the board, stones may not be moved, but stones are removed from the board if captured. Capture happens when a stone or group of stones is surrounded by opposing stones on all orthogonally adjacent points. The game proceeds until neither player wishes to make another move. When a game concludes, the winner is determined by counting each player's surrounded territory along with captured stones and komi. Komi are points added to the score of the player, with the white stones as compensation for playing second. And of course, games may also be terminated by resignation. So before I talk about Zero, I'm just going to talk a bit about Go and its significance. AlphaGo, the Go game playing software, was one of the most significant achievements in the field of AI. When AlphaGo defeated the world's best Go player, Lee Sedol, in 2016, the majority of the artificial intelligence community did not think that AlphaGo would be capable of such a feat. A lot of people would predicted that it would take at least another decade, or maybe even that they would never reach that level. AlphaGo, the system created by DeepMind, was taught the game of Go through the input data of 100,000 games of human experts. And it improved its capacities by playing the game with itself repeatedly, learning from a foundation of human methodology. Due to the human input it was exposed to, it was taught by the cultural education passed down through multiple generations and was informed to perceive the game through the foundational data and lens of how humans perceive this game. However, AlphaGo began to develop its own inhuman repertoire during its self-play training process and developed non-standard strategies beyond the scope of traditional human Go knowledge. In game 2 of the famous series against Lee Sedol, AlphaGo conceived a famous move that no one would, move 37. Commentators initially interpret this move in the game as a very strange move and a mistake, a move that took Lee Sedol around 15 minutes to respond. This move left the Go community incredulous, and it is now viewed as one of the most brilliant and beautiful moves in the history of Go. This move demonstrated how artificial intelligence can not only play a complex game at an unprecedented superhuman level, but that it can simultaneously showcase ways to reinvent its logic and its practice. Moreover, move 37 led Lee Sedol to conceive a move that would most likely not been made if it wasn't for the previous moves by AlphaGo. Move 78, a move famously described as God's touch. Based on Google's data, AlphaGo's bold move 37 had a 1 in a 10,000 chance of being played by a human. And we countered with innovative moves of his own, such as move 78 in game 4, which also represented a 1 in a 10,000 chance of being played by a human. AlphaGo led Lee Sedol and the Go community to new approaches and insights into the game of Go. These two moves are now part of the history and corpus of Go students, and they represent a harbinger of the ways that AI can shed new insights on human knowledge. AlphaGo was an impressive achievement, but it was not nearly as compelling as the abilities of a following system named AlphaGo Zero. AlphaGo Zero was the following version of AlphaGo Master. AlphaGo Master was a version created after AlphaGo Lee, and Zero was the following one. And it wasn't taught by any human input and didn't receive any data from human games or human-based concepts of what the game is. It essentially only learned the rules of the board game. In 3 hours, AlphaZero played like a human beginner, foregoing long-term strategy to focus on greedily capturing as many stones as possible. After 19 hours, AlphaGo Zero learned the fundamentals of more advanced Go strategies such as life and death, influence, and territory. And after 70 hours, AlphaGo Zero was already playing at superhuman level, presenting discipline and involving multiple challenges across the board. When in the beginning, AlphaGo Zero had absolutely no knowledge of the game and no input. Only the basic rules were given as input to the system. After 3 days, it surpassed the abilities of AlphaGo Lee, the version that beat the world champion Lee Sedol in 4 out of 5 games in 2016. In 21 days, AlphaGo Zero reached the level of AlphaGo Master, the version that defeated 60 top professional online and world champion KG in 3 out of 3 games in 2017. And in 40 days, it surpassed all other versions of AlphaGo and arguably becomes the best Go player in the world. It does this entirely from self-play with no human intervention and using no historical data. Around this point, AlphaGo Zero won 100 games, 100-0 to AlphaGo Master. So I'm going to explain how AlphaGo, how the algorithm works and how it differs from the AlphaGo Lee version of the system. The tree search in AlphaGo Lee evaluated positions and selected moves using deep neural networks. These neural networks were trained by supervised learning from human expert moves and by reinforcement learning from self-play. In Zero, they introduced an algorithm based solely on reinforcement learning, without human data, guidance, or domain knowledge beyond game rules. AlphaGo became its own teacher, a neural network trained to predict AlphaGo's own move selections, and also the winner of AlphaGo's games. This neural network improved the strength of the tree search, resulting in higher quality move selection and stronger self-play in the next iteration. This updated neural network is recombined with the search algorithm to create a new, stronger version of AlphaGo Zero. And the process begins again and again. In each iteration, the performance of the system improves by a small amount and the quality of the self-play games increases, leading to more and more accurate neural networks and even stronger versions of AlphaGo Zero. This technique is more powerful than the previous versions of AlphaGo because it is no longer constrained by the limits of human knowledge. Instead, it is able to learn tabula rasa from the strongest player in the world, AlphaGo itself. It also differs from previous versions in the following notable ways. Zero is trained solely by self-play reinforcement learning, starting from random play without any supervision or use of human data. AlphaGo Zero only uses the black and white stones from the Go board as its input, whereas previous versions of AlphaGo included a small number of hard engineered features. Zero uses 1 neural network rather than 2. Earlier versions of AlphaGo used a policy network to select the next move to play and a value network to predict the winner of the game from each position. These are combined in AlphaGo Zero, allowing it to be trained and evaluated more efficiently. AlphaGo Zero does not use rollouts, fast random games used by other Go programs to predict which player will win from the current board position. Instead, it relies on its high-quality neural networks to evaluate positions. Zero uses a simpler tree search that relies upon this single neural network to evaluate positions and sample moves without performing any Monte Carlo rollouts. Also worthy of note is that AlphaGo Zero evidences how algorithms are more significant than computational power and vast amounts of data. Zero was able to achieve such results using only 4 TPUs in comparison to the 48 used for AlphaGo Lee. Silver summed AlphaGo Zero's potential perfectly in his paper, Mastering the Game of Go Without Human Knowledge, by saying, and I quote, AlphaGo Zero discovered a remarkable level of Go knowledge during its self-play training process that not only included fundamental elements of human Go knowledge, but also non-standard strategies beyond the scope of traditional Go knowledge. Humankind has accumulated Go knowledge for millions of games, played over thousands of years, collectively distilled into patterns, proverbs, and books. In the space of a few days, starting tabula rasa, AlphaGo Zero was able to rediscover much of this Go knowledge, as well as novel strategies that provide new insights into the oldest of games, end quote. This is a transcendental form of technology that enables approaches that can overcome the limitations of the capacity of our biologically designed brains and the inherent cultural notions that humans have of what things are. Without rooted educational foundation based in our culture and previous concept of what things are and how to learn them, these systems can achieve tremendous results and present brand new notions of the ontological meaning of what a game is, learning by themselves from a tabula rasa starting point. This capability can bring forth a myriad of knowledge and an unprecedented insight into previously established educational knowledge that has mostly existed through previous foundations built on centuries of cultural and social development. These systems have the ability to approach concepts from an unstructural tabula rasa perspective, demonstrating new and more effective ways of learning and new ways of approaching and perceiving concepts that end up being rooted and formalized through culture. Thanks to this completely unchained, non-anthropological process, anthropological being an apt choice of word here, as it demonstrates that we humans are all products of our social and cultural upbringing in our environment and are therefore limited in our creativity and scope of perception. They can build foundations that are completely free from any pre-established notions. Moreover, it also enables the possibility to perceive and expand existing foundations, presenting new considerations and novel approaches towards them. These systems excel without human input and can bring insight to structural systems of knowledge that have developed over thousands of years through human cultures. Such methodologies have the ability to demonstrate new ways of interpreting and engaging practices, of expanding paradigms, and the way humans think outside of humanity's box. The premise of AlphaGo's analogy can bring forth a paradigm that instigates humans to hone on the socio-cultural and biological structural confinements that humans inevitably and biasedly exist within. Unsupervised learning can help to break through systemic structures of knowledge and invigorate the understanding of what understanding is, presenting new perspectives on human-made paradigms, not only in games like Go, but in a vast array of fields. And that's the end.
Okay, thank you very much. Would anyone like to respond to that, or any comments or questions?
I'd love to respond. I don't really have any sort of things specific to AlphaGo to say, but just that was a wonderful presentation, and sort of two things. Let's see, like sort of two things stuck out to me, but particularly just like the description by the Go community as that it's sort of initial move. I can't remember what number move, as like one of the most beautiful moves in the history of Go. I think just that description of sort of like beauty is really interesting, particularly as we kind of like think about the overall human-computer interaction or something. And I just like, on that note, and I think this is an interesting question, is like thinking about the sort of interaction of like a sort of new, like a new area of Go knowledge that's sort of quintessentially non-human, and like how that relates to the actual sort of human knowledge that we have about Go. And this is just my own sort of like thinking through it, but like I wonder to what degree like AlphaGo and these various sort of offspring of it like are even playing the same game as humans. I mean, like we could say like there's a set of rules and sort of you know, some sort of like taxonomy or something of Go rules that both the computer and the human agent are sort of operating within, but it's sort of unclear to me, given like a larger breadth, whether they're actually playing the exact same game when you sort of open up those rules to sort of other histories of how like thinking works or something like that. I'm not entirely sure, but this reminds me of the sort of like the idea of like myriotopology, which we talked about a little bit, like this sort of idea of like parts as being bigger than their wholes. And it's something that I actually don't know how to think about in a way. I'm not sure how that's different from topology, but just sort of remembering this Hinton quote of, you know, what can or cannot be sort of described in terms of thinking, what can or cannot be described in terms of this sort of high dimensional space, embeddings in this high dimensional space. So yeah, I mean, I guess I'll just leave it at that, and it's sort of a ramble as usual for me in these contexts, but I do wonder what other people think about sort of thinking in terms of this game as like this sort of like stack of computers not even playing the same game, but still having some sort of like topological encounter with the human players and their own version of Go. And then the fact that like this is described as quite beautiful from the perspective of the human tradition of Go. I think that's an interesting way that we frame, or that the Go community like framed that encounter. I think it's quite compelling. I hope that makes sense.
Yes, thank you.
Sure.
I think it is interesting because I think more so than with chess, there was this divergence happened actually a fair amount of time ago, because Go was certainly considered to be a very difficult problem, primarily because of the combinatorial explosion, which Guillermo explained well. That just the space to explore was just so huge, and people. And it was interesting because the progress that was made actually involved, in some ways, making the computer get dumber. Have I spoken about this before? The Monte Carlo methods?
Yeah, I think you spoke about it in the third week.
Yeah. So yeah, that in effect, they stopped trying to assess the board through heuristic, just sort of said, okay, let's just play random games and see what percentage of the time the board results in a win and what percentage of the time it doesn't. So in that sense, they were making progress by going away from anything we would consider human thinking. But then this approach comes around, which it makes some use of Monte Carlo methods just to thin down the state space, but it's also doing something fundamentally different, because it's abandoning sort of the idea of human taught strategy completely. Certainly with AlphaGo 0, arguably even in AlphaGo, but AlphaGo 0 is, I think, more philosophically profound, because as Guillermo said, you have this machine that effectively is just playing itself over and over again and training its nodes. And by the end of it, you have Go players are attributing all sorts of human-like qualities to it. And that's a remarkable achievement. You can consider it in some ways, okay, well, it's that I would argue is a lot closer to passing the Turing test than any of those, sort of conversations where a foreign a computer pretends to be a foreign kid and can sort of get away with fooling someone. But here, the computer's making moves that master Go players can't help but attribute some sort of psychological quality to. And certainly in the sense of strategy, it has incontrovertibly some sense of strategy. So how can we say with regard to Go that the computer has not picked up some sort of knowledge, some sort of conceptual grasp of what is going on? The difficulty, of course, being you can't open it up and see what it thinks. You can't talk to it. You can't ask it. And this is especially frustrating because when it makes these unprecedented moves, and in fact, it's making moves that are considered to be better than what a human player can manage. It leaves you at somewhat of a loss of saying, okay, what's going on here? Since it's based on this analogy and inspiration from brain-based neural models, how is it that we came up with something that does something different? And I haven't seen anything that even begins to speculate on that. And the question is there an answer to be had? Is there an answer that we can grasp? In the second silver, in the second silver paper, it suggests AlphaGo 0 may be learning a strategy qualitatively different to human play. That's a very that's a very loaded statement. It's saying, well, you know, certainly it is learning in the broadest sense, but how is that strategy being encoded into the nodes of its network? And I should say that while certainly computationally it's not consuming a huge number of resources, because of the exponential growth in computational power, it's still using far more resources than would have been available to it even a ways back. So while the development of machine learning method of the neural network methods is absolutely critical to it, it certainly it was required to at least have a certain degree of processing power as well, just not a huge one in terms of what we think of as huge processing power today. And so we're confronted by a problem like this where we've accomplished something, and unlike I think with Deep Blue, and it beating Garry Kasparov in chess, where there was certainly a sense that, you know, this was a remarkable milestone. It had been coded with so many heuristics and knowledge that there was, at least we still had some grasp of what it was doing. But now when you have a generalized mechanism, a much more generalized mechanism that can learn a game, and I believe, I forget what it's a variant. It's a variant of AlphaGo that also plays shogi and chess, I believe, and plays them all well. That we've actually.
There's also, sorry to interrupt. There's also a version that plays a very famous RPG game that's also supposed to be very complicated. That exists in these massive tournaments, team-based play tournaments, and it was also a remarkable achievement. I forgot the name of the game, but they also considered it to be just as complicated as Go. I think it had Dota, exactly. Yeah.
Yeah, Dota. Yeah. Yeah, that when you that if you constrain the context sufficiently, and so that the rules can be specified, then can you just have this thing simulate games over and over and over again to the point where it surpasses human performance, even though it has had no contact with anything resembling human thinking. It does dodge the issue that was raised earlier by Jesse, I think, about causation, because one can say that in Go, the causal relationships are, you can either say that the causal relationships are in effect built into the correlations, that you cannot have correlation without causation. The only way something happens in Go is if something immediately happened before it. So you dodge that problem. You've got a problem in which certain aspects of certain conceptual apparati are not required. So we have this marvelous achievement, and yet we don't know exactly what it is we've achieved. And if this is the wave of the future for AI, I think it says something either profound or disturbing or both about our ability to grasp our own place in the world and what it is that we ourselves do and how we work. Certainly, the history of psychology is in large ways the history of folk psychology, of boiling the brain down to a much simpler model than what it actually is. And AI may be helping us to realize that that not only have we been doing that, but the reality may perhaps be out of our grasp. Now, I just saw that Stefano's not going to be here today, so I wanted to go over quickly and ask, since I hadn't planned to speak, I hadn't planned to go over the deep learning book in detail, whether there were specific questions about the excerpts from the deep learning book, and how it does say deep learning of, let me put this up. Okay. The deep learning model in the upper right, and effectively the various layers of a deep learning model, how it can identify various components of an image, because as we saw, image recognition has been, I think, one of the most successful applications of these deep learning techniques. And I wasn't going to get into it with too much detail, because it is, in so many ways, it is an perceptron and PDP approaches. But I did want to ask if there were any questions.
David, this is a really simple question, but I can never remember what is the sort of base form of data that's being looked at, like in the context of image recognition? Like, is it the numerical values of each pixel?
Yeah, I mean, there's some flexibility, but in effect, you're feeding it. Ultimately, you're feeding it bitmaps of saying, okay, well, yeah, this pixel is this color, this pixel is this color, and there's some innate encoding where, okay, it's represented as, okay, well, I have this two-dimensional grid, and the pixels are arranged in such and such a way. This pixel is adjacent to that pixel, et cetera, et cetera, et cetera. That it is in effect hard-coded with the knowledge of those relationships, and this is in place of what one might call some sort of sensory modality, right? But the sensory modality can just be like a robot, a camera that looks and takes in and processes it in that way.
David, I was wondering if you could talk a little bit about distributed representations and
distributed what?
Distributed representations.
Yeah, we saw that we saw that in PDP in the PDP readings last time, and the basics of distributed representation is that it got, I think, let me see, there was some feature or some category is not represented in a single node or even a localized group of nodes, and possibly not even as a persistent organization, but as some sort of emergent being a tricky word, but some sort of process that occurs in the nodes in response to certain triggers. That, let's say the nodes are triggered in a certain way by seeing a set of pixels in a certain way, but if it's going to identify a cat in a picture, it's not that there's some single node or cluster of nodes that says, oh, okay, we've got these pixels and it's all a cat. More that there may be sort of, this is stripped down, but let's say, one part recognizes an ear, one part recognizes a whisker, one part recognizes some gradient between the edge of the cat's face and the surrounding environment. There's some recognition of the overall shape of the face, things like this, and all these are happening independently. One's not necessarily, no, in fact, one's not feeding into any other, but the collective result of all these nodes being triggered in recognizing those certain things flows into other nodes in other layers and eventually comes together to trigger a single output of cat. That's the basic idea of a distributed representation. Does that make sense?
Yeah, it does. I was asking because in the last readings, there's a lot of critique of the absence of the capacity of generalization in deep learning, for example.
Yeah.
But could we argue that this the fact that one feature can be a part of many representations be a seed to think about how generalization can occur in this type of networks?
That's a very good question. I think the only answer can be, the only possible answer, broadly speaking, is that some people would say definitely yes, and some people would say absolutely not. And I think that's the issue, is that you clearly have the issue of what is generalization, that you have generalization going on in some sense, in that these nodes are being used in a variety of contexts, so that they are serving a more generalized purpose in that regard. What they aren't doing, however, is ever saying, well, here's my whisker node. Maybe this whisker node and this other hair node, maybe there's something similar there. Now, it's possible that through retraining, maybe something like that would happen, but there's not really a science of it. So, and this gets into something I'll be speaking to later, which is, generalization is something you do with concepts. To what extent do these models possess concepts? And that is a huge debate as well. And let's see, should I move? What should I do here? Nikita is still not here, huh?
No.
Nikita. Okay. Well, maybe we should just press forward then. And sorry, but Hernan, did that answer your question?
Yeah.
Well, it's not answering your question, but it's speaking to your question, which is, yes, that in the same way, the irony, the symbolists say, well, you aren't working with real symbolic concepts here, you're just finding correlations. But then you get this irony that these methods generalize much better and can be applied to new situations much better, where the symbolic methods fall down. And that gives both sides, I think, a big headache in terms of, okay, well, we're generalizing, but we can't say what we're generalizing, or we don't know the limits of that generalization for the PDP side and deep learning side. And on the symbolic side, well, we're beginning with the generalizations, but and we can generalize more through explicit inference rules, but we can't be said that we're actually generalizing something that relates to the real world at all. And I will get into this more later. And maybe that's why I should just go. Let's continue. And obviously Gary Marcus speaks to this too. And I'll speak, we'll take a break, and then we'll do Marcus. How about that? And we'll have, and then we'll do Lipton. Okay, yeah. So okay. So okay, we conquer Go, and that's amazing. Now, what I want to say is that, and I was saying that this milestone is perplexing because we don't wholly understand why it does so much better. So in some ways we're really applying the functionalist idea again and saying, well, yeah, because it plays Go so well, it thinks it's a Go thinker. It just has to be. There's no way it can't be. So this vindication, in that sense, it's not quite philosophical in that way, or the vindication for PDP is not quite philosophical. You can argue that PDP was a theoretical vindication for perceptrons because it did serve as a rejoinder to Minsky and Papert's criticisms of perceptrons. There was now a theoretical rejoinder saying, no, perceptrons are actually, or perceptron-based PDP systems are far more powerful than Minsky and Papert maintained. But things were far muddier in the 1990s because the issue wasn't that that no one was proving that neural networks could not do something. It was just that neural networks hadn't done all that much yet. And at the same time, Deep Blue is beating Garry Kasparov at chess, and other machine learning approaches are generating decent, if not ground-shaking advances in things like voice recognition and spam filtering and other problems, primarily those dealing with noisy data and filtering. But you get this huge practical vindication, and suddenly deep learning, the extension of PDP methods to encompass far larger hierarchical networks and amounts of data orders of magnitude larger than anyone could have envisioned, as well as in the case of AlphaGo Zero, just larger amounts of processing power without larger amounts of data. But AlphaGo Zero is, I think, an outlier, and in large part you are looking at the application of huge amounts of data. But yeah, and this deep learning pulls ahead of the pack in concrete problems with immediate utility. And this utility is often a utility that wasn't even in problems that hadn't formerly been at the center of AI, like labeling images, recommendation networks. These are problems that only became priorities in the age of the web, when there was suddenly all this data that was frequently unlabeled, and there was a strong capitalist impulse to organize the data and process it in a way that would make it financially profitable. And the canonical case in terms of that profit seeking is Google AdWords, which is I think still the greatest financial success story of the internet age. Showing ads relating to whatever keywords a user searched for turned out to be the silver bullet answer to making money off the internet, and nothing before since has even come close to that single accomplishment in terms of sheer lucrative power. Not Facebook. I mean, people have done well, but I think people forget that AdWords was a revolution and sent everyone chasing to see if there was any other way to make that much money off of internet ads outside of search engines. You know, you could say that Amazon compares, but you know, Amazon is not making money algorithmically in quite the same way. They're selling products. AdWords is I think is something much more new in that way. And as far as I can tell, you know, there hasn't been anything of that order since then. So, but with this financial imperative, it's a stark contrast to what we'd seen in the 50s, 60s with the dominance of the military-industrial imperative to make smart machines before the Soviets did, which is where a lot of the symbolic AI funding was coming from. Now there's a much more, and that was in some ways, you know, that's where the term moonshot comes from, where he's trying to get to the moon first. Why? Because the Soviets are doing it. That there's more speculation involved, and there's more willingness to, I think, invest in projects even after there's some evidence that they aren't going to pay off. Obviously, that happens in a capitalist situation too, but the time span, I think, tends to be a little tighter. So you know, no longer is there this, so in the last 20, 30 years, no longer is this orientation to the loftier problems of thinking. Now, a lot of researchers want to make very strict quantitative and measurable criteria on specified hard problems. And the thing that makes it AI is that the criteria are still set by humans. Can an image be labeled in the same way that a human does it? Can we suggest that the completion of a phrase, as a human would complete it? And the thing is, the age of big data doesn't just enable lots of data coming in to be processed, but it also allows for the creation of these sorts of statistical metrics in the first place. And that's a very important theme I'd like to stress, which is how this deep learning paradigm has altered not only how AI researchers are attempting to create intelligent machines, but also the way in which we are measuring their success. I spoke earlier about the yardstick of intelligence and the variable yardstick of intelligence, and the difficulty you have if everyone has a different yardstick. And how are we going to define what it is to be intelligent, and how are we going to know if a machine is intelligent? Well, it turns out that, in fact, there is a way around this problem of relativistic definitions of intelligence, sort of. And it's majority rule. We don't have to do individual comparisons of the GPS problem solver's steps to a human's problem solving steps when it's trying to solve a problem in formal logic. We collect the data on 1 million people labeling various images, and then see if we can get a machine to mimic that as much as possible. It's the Family Feud approach. Do people remember the game show Family Feud?
Yeah.
I mean, it's basically the point of the show, engage with, the point isn't to get the right answers. It's to get the most popular answers to a question to a question that was asked to 100 people. So, if 100 people gave the wrong answer, you get the points. And the infamous version of this was, I think my father told name a famous, the Family Feud question was name a famous Alfred. And, they got Alfred Nobel and Alfred E. Newman and whatever, but there's one question I think wasn't showed up. And do you know who it was? It was Albert Einstein. So there you go. So, so there you go. That's your measure now. You got the statistic. If you got the statistic that enough people say Albert Einstein, that's correct, because we don't have the time to check these quantitative metrics. We're just measuring them. For some problems, this approach is absolutely fine. Everyone will think this image is a dog, for instance. And if you get a picture of, I don't know, if you get a picture of some wolf that looks especially like a dog, it's not the end of the world if the machine labels it a dog as well, because, well, that's what humans are doing. If it does better, that's nice. In some ways, maybe it's not nice. Maybe it actually means it messed up somehow. But for other problems, ones which involve issues of aesthetics or ethics in particular, or even issues of knowledge, with regard to conceptual knowledge, it raises a lot of troubling questions which are a bit outside our remit. But what I want to stress is, we lack the equipment even to construct these statistical metrics until computers got big enough to process and assemble them. Just the assemblage of a data set of human written numbers used to be a time-consuming task. People that you had to, and it was done because it was a pressing problem. Now, creation of these data sets is very nearly trivial. The deep learning era isn't just burst by the advancement of processing power or the refinements of these neural network algorithms, but also by the advancement of data collection. Without data collection, we would not have the data sets with which to train these neural networks, and we wouldn't be able to reinforce machine learning models when they do things wrong. In a way, we've returned to a meta-cybernetic paradigm in that we are once again dealing with an organism and its environment, but the irony is that the organism is the deep learning network and the environment is all the people who interact with it. Yes, dirt sheet. Well, this is, Yeah, everything floats to its own level. Yeah. And this is why I consider it a paradigm shift, because once you've changed the metrics for success so drastically, I don't think it's conceptually possible to say that you are dealing in the same problem space, even if the overall algorithms and networks are similar. The context has changed drastically. And I would argue, once again, that the necessary conditions for the possibility of intelligence have changed. And here, this was originally where I was going to ask you, Hiram, to present, but you do have this space where data is less important, and that's in the realm of unsupervised learning when applied to very strictly constrained problems like AlphaGo Zero. And AlphaGo Zero is very interesting, and they are trying to generalize it to other well-defined, strictly contained problems, but in a way, its success tells us less because it's avoiding some of the biggest problems that we've been seeing over the last 8 weeks, which is those of engaging with the real world in a generalized way. That we can generalize, that even though we may be able to generalize from Go to Go, chess, and shogi, and that's amazing, you're still dealing with in some ways with the same issues that confronted the symbolic AI people, which was they too made progress on these strictly contained problems like checkers, and it didn't necessarily indicate that they were able to make such advances when it came to the messier world of human language, human reality, and just the explosion of interlinked concepts that we learn growing up and interacting in the world. So I think actually, I think actually I'd like to take a break right here, and then we're going to come back and we'll do Geronimo's presentation. I'll speak a bit more. We'll do Jesse's presentation on Lipton, and Nikita is not going to be here, I think. And so we may even have some extra time to just talk about whatever and just wrap things up, which would be nice. So why don't we take 5 minutes or so, and I will see you shortly.
Great.
What is this? Familien duel.
I grew up with that as well, with the German version of Family Feud. It's trashy. It's incredible.
I mean, it really, you know, it's the very definition of populism, you know. It's really funny. I mean, I don't even know how the idea was come up with, because it's like, why would you even do that? I guess because, yeah, it speaks to the desire for whatever the majority of people said.
Yeah, some kind of certainty from societal certainty, I guess.
Yeah. Okay, I'll think on that. Okay, let's take 5. Let's take 5. Oh, actually, you know what? While we're gone, I'm going to put on, I hope I can do this. Are you able to share sound? I was going to put on a Magma video, since people were asking about this.
Also, David, today I found your Amazon account with reviews by accident. I found your review on a book.
Really?
And then, and then I found your list of, what was the name? It was the list that had the Blind Owl and Artaud writings. I don't know, but I stalked your Amazon account for a bit this afternoon.
Artaud?
Yeah, you had a list. I don't know. It was either mysterious books or.
Yeah. That list is actually from that list was from a Brandeis professor, and it was taken down when Amazon got rid of their list functionality, and I wanted to restore it because I thought those lists were so great. But those lists aren't by me.
Okay.
Okay, and now I will leave you with a little bit of magma while we take a break. Here we go. I hope. Is this coming through? The music?
It's very
You know, there
Oh,
might be
Volume is very low.
a copyright problem about this.
Aha, this will work. Does that work? Okay. I'll see you in 5 minutes. All right. I hope you all enjoyed Magma. Ray's favorite band. So
I just said in the chat, to me it sounds a lot like Zappa, but without the storytelling in a sense.
really, I mean,
My speakers at least.
interesting. I mean, I get, huh? I never really thought about it simply because like the cultural context is so wildly different, like to put it mildly.
Yeah, absolutely. Or like at least early mothers of invention, like from the the scales and the ups and downs and the little choir-like sections.
I wonder, I mean, it may be that, they're both coming out of, Stravinsky, Stravinsky in particular, that there's just a lot of sort of early 20th century classical moves that progressive rock became obsessed with around that time. I don't know. I don't know if any of you know Henry Cow, but like Henry Cow actually were probably both influenced by Zappa and by Magma and Stravinsky, and you hear Stravinsky just creeping through in everything they do, or even Universe Zero, if you know them.
Henry what?
Henry Cow.
No.
Of which Galen Strawson was briefly a member. Very briefly.
How do you Oh, a composer, Henry Cowell?
No, just Henry Cow. Like, yes, supposedly not named after him, but no, just Henry Cow, like the animal. Lots of like yeah, art is not a mirror, it is a hammer. They were Marxists. So. All right, let us continue. Where were we? How did I scroll down here? AlphaGo 0. Yeah, okay. So I was talking about in the Kantian, how in the Kantian sense, parallel distributed processing approaches and consequently deep learning approaches as well possess a remarkable faculty of judgment, of the sort of free play of classifying things in categories, as long as I think they are pre-provided with those categories. Unsupervised learning attempts to construct categories, but the results there have been a lot more mixed. But nonetheless, we can say, okay, faculty of judgment. Well, they seem to lack what symbolic AI people demand for a faculty of cognition, and this is the critique that that Gary Marcus makes. And with that, I would like to turn things over to Geronimo.
Yeah. Do you know how I can share my screen? It's in the bottom.
Yeah, there's a green button.
Okay. Are you seeing my screen now?
We're seeing you.
Not yet, yeah.
Share desktop. Yeah. Now you're seeing it?
Yep.
Yes.
Yeah.
Okay, so I'll be talking about Deep Learning, a Critical Appraisal by Gary Marcus. So Gary Marcus is a scientist, author, and entrepreneur. His research focuses on natural and artificial intelligence. Marcus is a professor in the Department of Psychology at New York University and was founder and CEO of Geometric Intelligence, a machine learning company later acquired by Uber. In Deep Learning, a Critical Appraisal, Gary Marcus presents 10 concerns about deep learning and suggests that it must be supplemented by other techniques if we are to reach artificial general intelligence. This presentation will follow Marcus's structure of subcategories, looking forward to give a theoretical rather than technical notion of the deep learning pitfalls. Deep learning is data hungry. Deep learning currently lacks a mechanism for learning abstractions through explicit verbal definition and works best when there are thousands, millions, or even billions of training examples, as in DeepMind's work on board games and Atari. In problems where data are limited, deep learning often is not an ideal solution. Deep learning is shallow and has limited capacity for transfer. Give me one sec. Yeah. Although deep learning is capable of some amazing things, it is important to realize that the word deep in deep learning refers to a technical and architectural condition built of a large number of hidden layers rather than a conceptual one. The representation acquired by such networks don't naturally apply to abstract concepts like justice or democracy. According to the popular YouTube video of a system learning to play the brick-breaking Atari game Breakout, after 240 minutes of training, the system realizes that digging a tunnel through the wall is the most effective technique to beat the game. It is important to keep in mind that the system doesn't really understand what a tunnel or what a wall is. It has just learned specific contingencies for particular scenarios. Transfer tests in which deep learning systems are confronted with scenarios that differ in minor ways from the ones on which they were trained show that deep reinforcement learning solutions are often extremely superficial. Deep learning has no natural way to deal with hierarchical structures. Most current deep learning-based language models represent sentence as mere sequence of words. The core problem is that deep learning correlations between sets of features that are themselves flat or non-hierarchical, as if in a simple unstructured list with every feature on equal footing. Hierarchical structures are not inherently or directly represented in such systems. And as a result, deep learning systems are forced to use a variety of proxies that are inadequate, such as the sequential position of a word presented in a sequence. Deep learning has struggled with open-ended interfaces. If a system can represent the difference between John promised Mary to leave and John promised to leave Mary, it won't be able to draw inferences about who's leaving whom or what is like to happen next. Current machine reading systems have had little success in tasks in which inferences goes beyond what is explicit in a text, either by combining multiple sentences or by combining explicit sentences with background knowledge that is not stated in a specific text selection. Deep learning is not sufficiently transparent. The relative opacity of black box neural networks has been a major focus of discussion in the last few years. In their current incarnation, deep learning systems have millions or even billions of parameters identifiable to their developers, not in terms of the sort of human interpretable labels that canonical programmers use, but only in terms of their geography within a complex network. Although some strides have been in visualizing the contribution of individual nodes in complex networks, most observers would acknowledge that neural networks as a whole remain something of a black box. The transparency issue, as yet unsolved, is a potential liability when using deep learning for problem domain like financial trade or medical diagnosis, in which human users might like to understand how a given system made a given decision. Deep learning has not been well integrated with prior knowledge. It's not straightforward in general how to integrate prior knowledge into deep learning system, in part because the knowledge represented in deep learning system pertains mainly to largely opaque correlations between features, rather than to abstractions like quantified statements. Deep learning works great in problems like speech recognition, in which there are a lot of labeled examples. Problems that have less to do with categorization and more to do with common sense reasoning essentially lie outside the scope of what deep learning is appropriate for. Deep learning cannot inherently distinguish causation from correlation. Roughly speaking, deep learning learns complex correlations between input and output features, but no inherent representation of causality. Deep learning presumes a largely stable world in ways that may be problematic. The logic of deep learning is such that it is likely to work best in highly stable worlds, like the board game Go, which has unvarying rules, and less well in systems such as politics and economics that are constantly changing. Deep learning works well as an approximation, but its answers often cannot be fully trusted. Deep learning systems are quite good at some large fractions of a given domain, yet easily fooled. An ever-growing array of papers has shown this vulnerability. A recent news story recounts the trouble a British police system has had in distinguishing nudes from sand dunes. Deep learning is difficult to engineer with. Another fact that follows from all the issues previously mentioned is that it's simply hard to do robust engineering with deep learning. It is comparatively easy to make systems that work in some limited set of circumstances with a short-term gain, but quite difficult to guarantee that they will work in alternative circumstances with new data that may not resemble previous training data, particularly if one system is used as an element in another larger system. Now that the main ideas are on the table, Marcus moves forward in the text to talk about possible scenarios of deep learning, like a potential risk of excessive hype. So he mentions that one of the biggest risks in current overhyping of AI is another AI winter, such as the one that devastated the field in the 70s. So executives investing massively in AI may turn out to be disappointed, especially given the poor state of the art in natural language understanding. Already some major projects have been largely abandoned, like Facebook M project, which was launched in August 2015 with much publicity as a general purpose personal assistant, and then later downgraded to a significantly smaller role, helping users with a vastly small range of well-defined tasks such as a calendar entry. Marcus' largest fear in the field of AI could get trapped in a local minimum, dwelling too heavily in the wrong part of intellectual space, focusing too much on the detailed exploration, potentially neglecting riskier excursions that might ultimately lead to a more robust path. Despite all the problems sketched, Marcus proposes to reconceptualize deep learning, not as a universal solvent, but as simply as one tool among many. In perceptual classifications where vast amounts of data are available, this deep learning is a valuable tool. In other, richer cognitive domains, it is often far less satisfactory. Unsupervised learning, as the term is commonly used, tends to refer to several kinds of systems. One common type of system clusters together inputs that share properties, even without having them explicitly labeled. Google's cat detector model is perhaps the most publicly prominent example of this sort of approach. Another approach proposed by Jan LeCun is to replace labeled data sets with things like movies that change over time. The intuition is that systems trained on videos can use each pair of successive frames as a kind of teaching signal in which the goal is to predict the next frame. The systems could set their own goals, and do reasoning and problem solving at this more abstract level. There is a chance to accomplish major progress faster. The remain areas from natural language understanding to common sense reasoning, in which humans still retain a clever advantage. Learning the mechanisms underlying those human strengths could lead to advance in AI, even the goal is not and should not be an exact replica of human brain. For many people, learning from humans means neuroscience. In Marcus' view, that may be premature since we don't yet know enough about neuroscience to literally reverse engineer the brain, and may not for several decades, possibly until AI itself gets better, and if so is the case, AI can help us to decipher the brain rather than the other way around. So just to conclude, deep learning is by itself just mathematics. None of the problems just identified are because the underlying mathematics of deep learning are somehow mistaken. In general, deep learning is a perfectly fine way of optimizing a complex system for representing a mapping between inputs and outputs, given a sufficiently large data set. Deep learning systems work less well when there are limited amounts of training data available, or when the test set differs importantly from the training set, or when the space of examples is broad and filled with novelty. And some problems cannot, given real-world limitations, be thought of as classifications problems at all. As yet, there is no general solution within deep learning to the problem of generalizing outside the training space. And it is for that reason, more than any other, that we need to look to different kinds of solutions if we want to reach artificial general intelligence. And that would be it.
Thank you very much, Geronimo. Yeah, I think Marcus gives a pretty complete, actually, would anyone like to respond to that? I think he gives a pretty complete rejoinder that encapsulates almost every objection I've heard made to deep learning. No responses?
Well,
Okay.
I think, oh, sorry.
Go ahead.
Just,
No, please go ahead.
just really, like briefly, I think some of the, I mean, a lot of these are, I think, explicitly, to one extent or another, engineering concerns, which are like perfectly valid, obviously. But also, I think, what I think he points out very nicely is the problem of mistaking one amazing advance for anything of actual like equivalence to how AI technologies or current AI technologies are used in like everyday life. So that's both a problem in terms of can these approaches be transferred in terms of the like operationalization of solving a problem to some extent. So transposing from one problem scenario to another, but also just like much more fundamentally to the issue of transparency and opacity, where, for example, in AlphaGo, we had an interaction where it was perfectly clear that the human in that scenario was interacting with an AI system. But further than that, the person was also a domain expert. It was a Go player, and not that, but like an expert, like a master, basically. So I think it's kind of important, like the points that he raises are important to keep in mind as like caveats to just reflect on when thinking about deep learning as like this amazing new paradigm that would bring about like a potential let's say maybe freedom or agency to go beyond causal capitalist logic or something like that. I think that it's really important to keep that these kinds of like caveats in mind in that regard.
Thank you. So yeah, I think you know, there is, you know, the standard response, I think, is, well, nothing else, you know, nothing else has worked. And that's one response. The other is that, you know, Marcus wants to move the debate away from the mind, because you can point to the mind and say, well, where is it that the mind encodes, you know, causation rules? Somehow the mind builds it up out of pure neurons. So that seems to be our theoretical argument that we could somehow do it with neural nets and deep learning. But is it that you just keep piling networks on top of each other, or do you introduce some organization to it? And that also harkens back to the argument we saw last week between PDP and the implicit argument between PDP figures and Chomsky, where they're saying, well, no, you don't, you know, syntax rules do not need to be represented explicitly or have switches in the brain. There doesn't need to be universal grammar. It can just be from getting weights. So the question is this bootstrap, can you get to this bootstrapping without adding anything else? It would be very nice if we could. The question is deep learning enough to get to this faculty of reason? Or has it already gotten to it? And some people seem to think so. This is on the deep learning book on page 5, where it says, deep learning solves the central problem in representation learning by introducing representations that are expressed in terms of other simpler representations. Deep learning enables the computer to build complex concepts out of simple concepts. And this was a picture, picture here, let me share it again. Okay. Figure 1.2 shows how a deep learning system can represent the concept of an image of a person by combining simpler concepts such as corners and contours, which are in turn defined in terms of edges. Deep learning is a particular kind of machine learning that achieves great power and flexibility by representing the world as a nested hierarchy of concepts, with each concept defined in relation to simpler concepts and more abstract representations computed in terms of less abstract ones. Now, there's quite a bit of conflation going on there. The key being that we are that this hierarchy of layers in the network has a one-to-one correspondence, at least a loose correspondence with a hierarchy of conceptual knowledge. And let's compare this to the LeCun paper on page 438. I can share it out. Let me see. Page 438. I don't need to share it. Okay. But yeah, on page 438 of the LeCun, Bengio, and Hinton paper on deep learning, he says, deep neural networks exploit the property that many natural signals are compositional hierarchies in which higher level features are obtained by composing lower level ones. In images, local combinations of edges form motifs, motifs assemble into parts, and parts form objects. Similar hierarchies exist in speech and text, from sounds to phones, phonemes, syllables, words, and sentences. This pooling allows representations to vary very little when elements in the previous layer vary in position and appearance. And yes, yes, exactly. Yeah. But the thing is, you know, the slippage. LeCun talked about signals being, both of them are talking about hierarchies somehow representing mental knowledge or mental processing in some way. But LeCun talked about signals being compositional, while Courville, Goodfellow, and Bengio talked about concepts. So I think we've returned to Hobbes all over again, with the computational being turned into the conceptual. For Hobbes, it's addition all up the line. And so it's vector space partitioning all up the line for some deep learning practitioners. And again, there's an ironic unity here in which deep learning and by extension the PDP techniques have made a similar collapse in layers of meaning as the symbolists did. With the symbolists, we saw that to them the possession of a concept was defined by a system possessing a symbol for it, along with formally defined relationships with other symbols. This is the physical symbol systems hypothesis. The symbolists criticized PDP and subsymbolic methods for having no way to get to this vaunted Gestalt level of semantic meaning. And symbolic AI ultimately went into decline because it could not put its supposed possession of conceptual meaning into actual practice. No matter what they did, it seemed their programs would generate something illogical, like dogs being unable to have 3 legs even after being amputated, or a man holding a light bulb being electrified. You know, there's something that would cause them to fail some functional test, Turing style, of genuinely holding on to a concept and knowing how to use it. The Turing test of how do I know, you know, how do I know what a dog is? And even today, deep learning claims to have partly overcome that problem. While LeCun and his co-authors start with signals, he also slipped into a more semantic realm, and it's most vividly on display when he talks about machine translation, because as is so often the case, moving into the realm of human language trips up attempts to outline human intelligence. This is on page 441. And is there, yes, there is a image to share. The image in the bottom right corner specifically of grouping words, word vectors. He says, if a particular first word is chosen from this distribution and provided as input to the decoder network, it will then output a probability distribution for the second word of the translation and so on until a full stop is chosen. Overall, this process generates sequences of French words according to a probability distribution that depends on the English sentence. This rather naive way of performing machine translation has quickly become competitive with state-of-the-art, and this raises serious doubts about whether understanding a sentence requires anything like the internal symbolic expressions that are manipulated by using inference rules. It is more compatible with the view that everyday reasoning involves many simultaneous analogies that each contribute plausibility to a conclusion. Okay. So in other words, by grouping, you know, we can like group. I think someone raised the I forget the example at any rate, but yeah, what LeCun says here is true, strictly speaking. Machine learning approaches have done better than machine translation with any other. But in large part, this is a measure of just how poor machine translation is. Machine translation has been. It's just not. There's not been anything like the rate of success you have in image recognition or spell correction or things like that. Translation is a much more semantic problem, and symbolic AI, based on what we've seen, has just has no chance in this realm. And so LeCun's criticism of a neo-Chomskyan symbolist approach has some bite to it. It posits that translation should, Chomsky is saying translation should be accomplished using explicit specified transformation rules. But, without getting into the weeds, there's less justification for LeCun and his co-authors' contention that you can pile up probabilities until the most reasonable possible translation pops out of a subsymbolic neural network or other similar model. That is sufficient. You can draw an analogy here between two ways of speaking in a foreign language. The first is where you first learn a language, take a phrase in your native language and find equivalents in the other language. And the other is when you internalize the foreign language sufficiently that your thoughts or concepts originate in that foreign language to begin with, or seem to originate in it as far as you can tell. These do seem to be two different mechanisms, and while the former appears amenable to being captured by a symbolist style approach, it's not clear at all that the second one is. And the problem in my mind is that of let's see, of not wholly being able to specify the inputs. The difficulty in machine translation lies in the problem that any sentence is at least partly embedded in a larger context of social practices and dialogue. And while deep learning approaches have the ability to assimilate a tremendous amount of that context sheerly through sucking up all the data into its vector space, the deep learning approach currently hopes that it's sufficient to throw additional layers of hierarchy at it and additional layers of nodes, and that context will suddenly pop out, being contained in a mostly unobservable way in the resulting network. That's how they hope cognition will happen. But most of the translation, even the machine translation successes you see with deep learning tend to be fairly mechanistic. They're translating phrases that have very exact equivalents and that don't rely hugely on context. If you feed it a paragraph of dialogue or something, it tends to fall down pretty quickly. It's only when you regiment sentences into very, very standardized forms. There was one where they were trying to summarize the Hobbit, and it would say, oh, actually Lord of the Rings, and it was like, Frodo went to Mount Doom, then Frodo went home. Where is Frodo now? And the machine learning can say Frodo is at home. But if you change the language at all, it can't do it. And the question is if you just keep on clustering relationships in that way, can you eventually get it to the point where you've approximated something resembling semantic meaning and pragmatic usage, or whether there's some greater step that's required that isn't going to emerge from these techniques applied in greater amounts of depth or hierarchy. I think that in many ways, the hierarchy of layers is a very appealing argument, because it says, okay, yeah, sure, this pattern recognition isn't sufficient on its own, but what if we have layers and layers and layers of pattern recognition that are increasingly more general? Does that somehow get us to these concepts? And I think LeCun would say yes. Marcus obviously says no. You know, the rejoinder, however, to critiques like Marcus's is that symbolist approaches seen a first idea of translation, of thinking consciously through a translation, and that doesn't seem to reflect what actual language acquisition is like. So if the pattern recognition, deep learning approach isn't sufficient, what is it that the mind is doing that makes the magic happen? Marcus wants to say, well, we just don't understand enough about the mind, and so we shouldn't be about the brain, and we shouldn't be looking to it for guidance, because it's just we're going to rat hole on it. But the rejoinder is, well, you know, you also don't know how it works, and since deep learning is getting far better results, we should stick with it and cross our fingers and hope for the best. I don't think that's such an unfair position as long as you make it explicit. It's when you start slipping into saying that these networks possess the concepts that you've gone too far, because you don't necessarily have that proof. And before I speak a little bit more on concepts, I wanted to turn it over to Jesse to talk about something very closely related to concepts, which is models, which are, one can say, are made up of concepts. So Jesse, would you like to take it over? Unless Nikita has suddenly appeared, which he hasn't. Okay, yes, Jesse, it's on to you.
Okay, thank you. I was kind of thinking that I was going to speak more about interpretability, but I guess I'll just give it a go.
Yeah.
Okay.
Model interpretability or machine or deep learning interpretability. It all works. It's all good.
Okay. Hang on.
Opacity is another, I should say, opacity is another huge problem, which I think we've spoken to here and there. Just not knowing why it is. We saw that with Go. All right, Jesse.
Okay, hang on. Okay. All right. Okay, everybody can see my screen? I think so. Okay, so this paper is really interesting, and Lipton in particular is quite an interesting guy to also follow on Twitter, or just look what he's up to, because he's, I think he's quite young. He's a professor. I don't exactly remember where. I think it's San Diego, at least he still is on this paper. But he's like a little bit of a rogue in the current machine learning community. Like he spends a lot of time talking about some of the basic assumptions that people have when they build these systems. And this paper is quite interesting, coming as it does at a time when the opacity of machine learning models was like a major thing, and it still continues to be so. Particularly the ways in which these kinds of, as David said, these kinds of, like, rather than having pre-specified rules, you kind of have functional approximations of rules from high-dimensional vector spaces that you can't look at as they are derived, or you can't really say why were these paths chosen rather than others, and how specifically are they come to be. So what's interesting about that paper, and it's from 2016, is that it comes, like I said, at a time where this started to become a major issue, and it's still like the hot topic in specifically human-computer interaction research, as we will see, because it immediately relates to topics of, for example, representation that we already had in a couple of seminars ago, and also representation both in terms of how can we even represent the apparent causal chains that are going on in these spaces, but also when and how can we do this for what kind of people? It's all pretty complex and not only technical questions. And one notable reoccurrence that we have, that we talked about, symbolic AI and cybernetics, of course, is that also with this topic, DARPA steps back on the map in a quite major way. There was a huge funding announcement by DARPA in 2016 that calls for explainable AI. And if we look at their use cases that they're interested in, it's pretty clear why, because they wanna or are using machine learning in, for example, satellite imagery detection and in drone piloting. But at the end of the day, in these kinds of scenarios, they want to some extent have a kind of, not necessarily human oversight, but they want to at some point have a human agency that then can decide based on, here it's called explainability, or I'm just going to use interpretability, what appropriate action to take based on how the model that is currently used more or less explains itself. And that is the huge issue that's starting here. And Lipton kind of looks back at a lot of this discourse that happens throughout the years. And it's really fascinating, especially looking from a humanities perspective, that interpretability is treated extremely vaguely in general in the community. And it's really, really interesting because sometimes it doesn't have anything to do with human interpretation at all. Sometimes it doesn't even mean machine interpretation. And sometimes it refers to intrinsic interpretability, so to speak. So can we actually think about what the model even does? Or it's talking about what Lipton here calls post hoc interpretability, which seeks to deploy algorithms to, so essentially further machine learning models to explain the model that arrived at a decision. So they're trying to use simpler models such as linear models to try to explain what the model does. So Lipton kind of offers this graphic here, which kind of already points to it, which is pretty cool. This interpretation box that happens between the black box and the human. So he basically has the qualm with the field that interpretability is never really rigidly defined. It's either taken to be just some random quality that is derived from general performance metrics, or it's something that isn't, it can't be formalized in the sense that other metrics can be formalized during the development. And he speaks to some issues that are quite similar to the paper that are that deserve some attention, and some of the reasons that make interpretability a desirable goal. And for example, trust, if a system, if a machine learning model makes a specific type of decision, on what basis could you trust that decision if you don't know for which reason, or even on which kind of basis it has arrived at that decision. Transferability is in a sense very, very similar to what was said in Marcus. And one point here is fair and ethical decision making, which I'm not going to get into, but basically he also distinguishes between, which I think is a very useful line to draw, between the transparency of the model itself and the transparency of the, or at least the minimizing the opacity of the output of the model, which is I think an important distinction. So on the one hand, he groups this under transparency, saying transparency is the opposite of opacity or black boxness. And then he goes into distinguishing that one feature of transparency would be if you were able to theoretically at least do the same computation by a human that the model takes out. So if we think about for example, the more like quantitative, like bag of words algorithms and things like that. Then he says the other one is decomposability, which is about, sorry, kind of losing my track here a little bit. Oh yeah, which is a little bit more about the inputs of the machine learning pipeline, and then about the technical specificity of the actual algorithm at play. And then the thing that I kind of want to talk about a little bit more is the post hoc interpretability, just because it's also in my area of interest. And it's a really, really interesting problem. Because it speaks kind of to a lot of the basic assumptions of also deep learning or machine learning more general, is that it has some sort of output, but we really, really want to be able to understand how it has arrived at the output, and what specifically is going on the way towards the output, or how data has been transformed and how functions have been approximated on the way to a specific output. And he Lipton discusses some basic methods that could be used. And for example, text explanations, which you can see in some papers as if a bird has been detected, then the technique for text explanations tries to literally generate a text where it says, this is a bird because it has wings and feathers, which are kind of like these concepts that have been extracted from the model and trying to be arrived at through inference. Visualization is a very, very common example of other approaches. I'm going to show an example of that in a second that kind of shows what that's about. And the other one is local examples, which try to point out how specific instances have been classified or modeled or patterned. And I'm just going to go for a second to this example, which is pretty cool because you can actually play around with it. I'm going to post it in the chat a little bit. So this is a typical kind of approach to interpretability. And one thing that is quite interesting is that almost all of the research in interpretability happens with visual material, visual data, so to speak. So it's incredibly oculocentric, which is kind of funny because obviously that's the easiest thing to show with a neural network in a sense. It's the easiest attribution to think of the individual neurons and pixels and so forth. So, but what happens here is, what's happening here? Oh, somehow it broke. 1 second. There we go. Okay. So what we have here is the researchers, in this case, they extracted, and you see these kind of weird deep dream kind of little layers. So they extracted features from the layers from the neural network, which in this case is a convolutional neural network, and then try to calculate which features in the neural network processing have led the particular machine learning pipeline to classify which parts of an image have led the neural network or have led the model to classify parts of the image as belonging to a tiger cat or to a Labrador retriever. And this is kind of like a very typical example of work that happens in the interpretability section. And this is a pretty cool approach that you can have a look at here. And they try a whole bunch of different methods that look at the kind of reasons for why the model thinks specific detections are reasonable or can be made. Right. So an interesting thing that has also occurred from interpretability, and this is directly related to his point that post hoc interpretations can potentially mislead, which I found in my research occurs all the time. And there have been a couple of papers about how even if you're trying your best or the most advanced techniques, such as deploying another model to explain the first model, what usually happens when you actually present users, even experts, even machine learning experts, with the kind of interpretability outputs, what happens is people tend to trust the model even more, even when it's the wrong outputs. That's actually what happens. So for example, there was a paper that literally randomly told people how confident an algorithm was in its output, and people believed it no matter what. So just because you can, to some extent, explain what is going on, it doesn't actually mean that a kind of access to the reasons or the reasoning processes of the model is somehow immediately available. And I think in terms of what David, you just said, this really kind of, I think the research trajectory of machine learning interpretability or model interpretability more general, if you look at it from like a meta perspective, it's really interesting how this is kind of like a struggle of really trying as much as you can to find that there must be some sort of concepts here. Like there must be some sort of semantic kind of like valuable features that are at play here. And maybe on a more, even more broader notion, I think what's really interesting about this is like, it shows that if you think about the current approaches from a historical perspective, is that what we're still looking for is some kind of stability, some kind of like reasonable, whatever that means, statement about the world that we can mimic with these machines. So we're still kind of living in this like long tail of teleological kind of deployment of these technologies, which I think is pretty fascinating and kind of like interesting to put into perspective, maybe. That's my take on that.
Thank you very much, Jesse. I think I like Lipton's paper, and I think you did a good job at drawing out the several layers of confusion that have emerged around. We're confused as to what they're doing, but we're also confused as to how to classify that conclusion and explain how that confusion could be addressed. And as Lipton points out, there's a laundry list of terms, and I have had a devil of a time trying to parse them. Let's go through a bunch of them. Opacity, transparency, explicability, scrutability, interpretability, intelligibility. Those concepts are not well defined. They have all been used in some way in the more general realm of explainable AI, to try to say, okay, well, how can we have AI explain itself? But as I think,
sorry, and not to mention fairness and accountability.
Yes, which are more which are well, those two, I think, in particular, draw out the problem that we don't even know how to have humans behave according to these metrics. That, you know, how on earth are we going to have AI explain itself if we aren't able to explain ourselves? And I don't know that there's a great answer for that. That's not a frivolous question. I think it is that in many ways we are setting a bar that we not only do we not meet most of the time, but that we don't even know what it would mean to meet. So
I forgot one citation from Lipton that I think really frames this quite well. So I'm just going to briefly read it out. So from his perspective, really at the end of the conclusion, when we have solid problem formulations, flaws in methodology can be addressed by articulating new methods. But when the problem formulation itself is flawed, neither algorithms nor experiments are sufficient to address the underlying problem.
I think that that speaks to so many of the themes of this course so directly that and of artificial intelligence more generally, that this junction of this seemingly anthropocentric human conception of intelligence with the industrialized mechanistic tendency has basically created I think a very fruitful confusion, but it's one that we're still trying to sort through. And to elaborate on one particular point, there was some mention of adversarial examples in Buckner, I think, but Melanie Mitchell's book actually has a better set of them. So I'm just going to share this out right now. Here we go. So in adversarial machine learning attempts to fool the networks by deliberately constructing examples designed to trip them up. And here you can see 8 images that were classified with extremely high confidence by a convolutional neural network. Now, I don't know, how do they look to people? Do you see the peacock?
No.
No? Okay, well, the interesting thing here, the even more bizarre thing is that they've done some tests where they show these images to people and they say, okay, and the people say it's garbage. But then they say, okay, well, if you had to pick one out of these, which one would you pick? And they do better than chance. so I guess that's the best counter argument you've got. It's like, well, there's a panda in there somewhere, clearly. But nonetheless, it does provide at least a decent intuitive counter argument to say, look, there's something missing there, or something about this processing is weird. Now, whether that can be just on the layer of how features are detected and things like that, that could well be true. I mean, certainly we fall prey to optical illusions, so it is not outside the realm of plausibility that perhaps the errors being made are simply errors in kind rather than in category. However, it's still pretty funny. So I thought I would share that. I don't know. Yeah. I mean, it's funny because you can look at it and you can sort of make out something. It almost starts to look like one of those like magic eye 3D images, like something's going to pop out there. But it still surprises me that that people could actually classify these with greater than chance. Oh, thank you. Yeah, great. Okay, so we're nearing the end of this. So a few concluding remarks about what we've been dancing around. These images, when you look at a picture of garbage and ImageNet decides that it's a panda, that makes you think it doesn't really know what a panda is. It may use the word, it may classify stuff as pandas, but somehow it lacks that knowledge. It lacks that gestalt. It lacks that concept. But what is a concept? And I think that at the end of the day, that is the question that faces it. And if there's one thing that I think this whole course has been leading up to, it's that the necessary condition that it regards, again, that transcendental question of the necessary conditions for the possibility of intelligence. And by intelligence here, I mean intelligence that includes the criteria given in the cyberneticist's ability for an organism to survive and stabilize itself, in the sense of the symbolist's ability to specify, break down, and solve problems, in the parallel distributing processing idea of a system that can recognize patterns through loosely connected components working independently, semi-independently, and in deep learning's approach of a network quantitatively matching human performance on specified tasks. That the necessary conditions for the possibility of all these sorts of intelligences, these specific intelligences, whether we want to call them intelligence or not, they all aim at a more general form, which we can hypostatize, which is the intelligence as the ability to formulate and manipulate concepts. Concepts which can be represented by symbols, linguistic or otherwise, but which are not entirely captured by those symbols. Concepts which exist in a fabric of overall human or animal existence. And here I mean survival or homeostasis is as much a concept as any other. But ironically, survival becomes a simpler one than a concept like dog, because the functional criteria then for knowing how to survive, you know how to survive, is in fact simpler than the functional criteria for using the word dog correctly in sentences and interacting with dogs in a way we recognize to be sensible. Staying alive, we know whether you've done it or not. Using the word dog correctly takes a lot more examination. The possession and employment of such concepts probably comes closest to a refinement of what Turing had in mind when he came up with his imitation game, the Turing test. In order to convincingly imitate human speech and human behavior, there's ultimately a necessity of possessing concepts. But unfortunately, concept remains underspecified, and ultimately concept is at the heart of what everyone is hoping will emerge from the efforts of whatever AI paradigm is being pursued. And so we return to Kant, because categories serve as a good proxy for what I'm terming concepts. They're symbolically linked, but they have a richer cognitive role than pure symbols. Yet we don't know whether they can pop out of a deep learning sea of conceptual knowledge, or if some other mechanism is required, either to organize that sea beyond the beloved partitioning of machine learning practitioners, or to learn in a way different from what any machine learning network does today. We can say that the learning done by networks doesn't capture all of what we mean by learning, but the question remains, what other sorts of learning are there? And so I want to conclude on the archaeological note that across these paradigms, it seems that the most elusive transcendental condition for the possibility of intelligence, of many different varieties of intelligence, though not all of them, is the ability to learn concepts. And that elusiveness is captured in the very fact that we have not yet fully defined what learning is, and nor what concepts are. Thank you. That's it. I had planned for 2 more presentations, so we have a little extra time left. So I think I want to open it up to just an open forum of discussion of whatever anyone would like to talk about. Questions, comments, reflections, you name it.
David, I was wondering, I was reading the Clark piece, predictive processing and generative models. I was wondering if you could draw out some of the philosophical implications, because I found that very shocking. It was very interesting.
It's really hard to say, because it's still theoretical, so we haven't seen what happens. It's, you know, it takes what we've been discussing in a different direction by saying, well, instead of trying to figure out these things in practice, let's move to something of a cybernetic approach of saying, well, you know, can we get this machine to anticipate and, you know, quote unquote, survive in a way through modeling and predicting. And this leads to arguments about free will and things like that, that, you know, okay, you know, is there something that effectively is working in us before before we even cognize. And I know that Clark is a big fan on this, but personally, I remain uncertain whether whether integration of this is going to lead to the sort of conceptual realm that we've been addressing, or whether it may be or whether it may be something that on the one hand offers a better model for the opacity of the human brain, and on the other divergently offers a machine learning model that does not in fact replicate what the brain is doing. And I'm sorry if this is unclear, but I think it is this interesting approach to sort of drag what one might call, I don't know, pragmatic content, I don't know, something like that, into what was thought of as a sub-symbolic layer. But I should probably read more as well, because I remain uncertain as to how those expectations are actually cashed out, or how they could be cashed out in artificial machine organisms. So I don't know. What do you think?
No, I was wondering if there might be a relationship that could be made between the internal models, the models that went out,
Yeah.
with the SCM, is it the structural causal models that Pearl is talking about? There's the causal machinery that he wants to embed in machines, so as to they could make this sort of more.
That is exactly the question that I myself wonder about. I don't know. Likely it can do so in some cases. Can it do so in a generalized way? I don't know. But, I think in some ways it does, it's making this claim to be, well, this is the next layer up. You don't just keep throwing additional layers of convolutional neural networks, or you build this sort of, you build a somewhat more theoretical explicitly model constructing layer. And I think that's very interesting. And certainly it gestures towards something like what Pearl is saying. But I'm not, but whether, between the Scylla of the symbolists' unwarranted abstraction and the Charybdis of the fingers crossed hope for emergence of the deep learning people, I'm not sure whether it actually steers a path that will get it through those.
One thing that I wanted to add, what I think is really interesting about predictive processing, in a sense, is that it's kind of like, again, like looking at it from like an epistemological view, it's kind of like, again, like a chicken and egg question. Like, for example, a coworker of mine is a machine learning expert, and he immediately, when he first read Clark, he immediately seized on it, not so much as something that is explicitly new to him, but just a kind of framework that allows him to build systems with a view to both the human and the machine learning side of it, basically. So as more of a governing principle of human-computer interaction in a sense, which is kind of interesting, I think. So I'm kind of wondering if that possibly, I mean, as machine learning begets this paradigm, and maybe the paradigm or part of it is begotten by machine learning or whatever, is reintegrated as a foundational principle or something like that. What kind of the epistemological cascade of that might potentially be, if there is one, if it doesn't just disappear over time.
I mean, I get, I want to say that in some ways it really does depend on how it plays out, because we've seen that technology has been such a conditioning force on not just on the accomplishments of AI, but on the very definitions that we've been using. So it may be that what we're waiting for, that predictive processing awaits the so-called killer app, that it does what is that? Is it going to be a military application? Is it going to be some application that actually like fixes the problems that you were talking about, Jesse? Will it be something that has to do with biotech? Will it be some form of ecological or environmental management or of social control? That depending on which of these applications it comes to be used in, that may end up conditioning what falls out of it epistemologically. And I think that is what makes these questions in some way unanswerable, because there are such historically conditioning forces on them, that we have a greater chicken and egg problem, simply in the sense of, we've seen that philosophy is very important and keeps getting smuggled in to these discussions and either ignored or taken for granted. Yet at the same time, we've seen how historically contingent those particular positions are on whatever it was that was considered important or pursued at the time. And so there's so many of those factors that I want to say that, even what we would say in a somewhat detached form such as this is going to be contingent on how that history develops. And I'm sorry if that sounds like a dodge, but I think that it is unfortunately true. That, Hegel's end of history or whatever is not a prediction you should make, and you shouldn't even make more modest predictions than that, because because the inputs to what the result are going to be don't yet exist.
David, sort of on that note, I'm wondering if you could speak to I know at the beginning of the class you talked about archaeology like as a method in terms of sort of like what Foucault meant. Mm-hmm. And I don't really know what exactly Foucault's position on that is. But I'm wondering if you could speak like a little bit now, like at the end of the course, like what like an archaeological view of this sort of development does or does not do for the way that we can sort of look at this tech. And you don't have to answer the whole thing, of course, but like specifically the way that we can view this tech balanced between these sort of like contingencies as you're talking about, and also like a critical stance on like a mode of production.
Yeah, I mean, Foucault meant it, I think, in a more structuralist sense that I mean it, because that I think he was more amenable to sort of this post-Levi-Strauss and Barthian view that, there are some, identifiable systems and rules that are measuring how, knowledge and concepts develop. I'm not going that far, but I think the method of looking for these conceptual underpinnings that are sort of taken for granted and how they change, which is why I started off with all those prehistorical readings from hundreds and hundreds of years ago, is actually very useful in grasping these movements, such as, here an archaeological move from my perspective, is that of looking at Hobbes jumping from calculation to cognition and saying, oh, okay, you know, there's this move that recurs. Now, is that move a part of some like inevitable like process of the history of thought? Well, I'm not going to go that far, but there's a lot to be extracted, I think, from these primary documents, and you see it in, I think, not just in Foucault, but you see it in, especially in Ian Hacking's approach to the work on his work on probability and chance and statistics, which in many ways presages deep learning in particular, since those methods are so statistically oriented. Information theory and cybernetics as well, to a lesser extent. But if you have a chance, you know, I think Ian Hacking's first two books in particular, what are they called? The Emergence of Probability and the Taming of Chance. Both are excellent books, and are well worth reading, just in that they perform, I think, a similar analysis as we've done here, except on ideas around chance and probability, which literally did not exist 1,000 years ago. People did not conceive of chance events as having like probabilities that something would occur, you know, with more likelihood or another in some sort of specifiable way. And then you start getting it through, you know, well, Bayes is a big, Descartes does it a little, Bayes does it a lot, and there are others. So what it has to offer, I think, is hopefully a way to clarify the massive confusions that we've been seeing. That we've seen that the same conceptual problems keep coming up, and people are sort of attacking them in different ways, and the contexts are shifting. So as far as identifying recurrences versus novelties, I think it's very useful there. And that's why I can say this processing can play itself out, is likely to play itself out in certain ways, but at the same time, there are contingencies that make say the epistemological implications of it are not yet knowable. I don't know that. I'll take a look at that, Jesse.
Yeah, I was just really briefly. I know I've spoken really a lot, but just really.
No, it's fine. It's fine.
Okay, so I can definitely recommend, just on what David was talking about, on the methodological usefulness of doing this kind of like deep dive. There's Davo Löffler, who's also a lecturer, or was a lecturer. He was gonna, I think, also be at the symposium, but was sick or whatever. He, in his German book, which isn't available yet, translated, but basically, and this paper that I posted to the chat is kind of like an extremely condensed version of that. But he does this exact thing. So he looks at how, not necessarily only from a technological perspective, but it's all entwined. So he looks at kind of like qualitative civilizational shifts, and whether you can kind of extrapolate how onto epistemological notions have shifted in those occurrences. So looking at ancient Greece, the Renaissance, the Industrial Revolution, and now to what he now calls this new axial age that we're in. And I think it's
new axial age.
Exactly. Yeah. Right now. I don't know if you knew, but right now. Yeah. No, it's brilliant. And I think what's really worthwhile about this, so from my kind of like post-phenomenological perspective, is that you can look at, there's this concept of like the micro-perceptual of the here and now of our daily bodily encounters, and the macro-perceptual, so kind of like the broader frames of reference that are mediated in those in the day-to-day, so to speak. So what's interesting, if the hope of these kind of deep dives and looking at kind of like patterns and recursions that happen in these shifts, is that you potentially can identify how, for example, shifts from the micro to the macro kind of keep on reoccurring. So like the SAI of yesterday is the micro thing of today, and things like that. And then hopefully, ideally, extrapolate from that and think about, okay, how can we do things differently, potentially, if there's such a thing as getting out of it. But I mean, that's kind of, I think, to a large extent, the premise and promise of doing this kind of stuff.
Interesting. I will take a look at it. Yeah, I just grabbed the paper, and there's an interesting chart that is certainly would make some people happy. This is the chain of production of and hunting with a bow and arrow.
Yeah, so that's one of the patterns. Like if you look at, originally you have the napping stone, and that's a comparatively very short operational chain, so to speak. Then, but as you go from the napping stone to the spear, to the bow and arrow, to whatever the next thing is, you have this kind of like recursive integration of operational chains that kind of keep making these things ever more complex, which is like one of the interesting patterns to look at, for example.
I will check it out. What is structuralism making a return? Is this the new structuralism?
I don't think he would agree with you on that, but maybe we should.
Probably a dirty word, I imagine. Yes, I'll be careful. Okay, well.
So,
yeah.
Can we keep talking just for a few moments, or?
Oh yeah. I mean,
okay. Because I'm wondering, like, for me, and I think it's sort of hard as like a graduate student to sort of get a feel for like the media studies, like, and what's going on sort of outside of media studies discourses, because everyone seems to have their own opinion, and inside of those opinions is like 100 opinions, which is fine. But I think, like, I don't know, to me, like, it's hard to navigate between, in my opinion, two sort of positions. And one is sort of interested in history, and maybe like as a subset of history, like a critical ability to like observe compressions. And this is where I would put someone like Galloway. And then on another side would be like maybe like difference in sort of an unclear mode, and like the ability to observe contingency, like the critical ability to observe contingency within that mode. And that's where I would put someone like Parisi. And like, it's sort of hard to like to look at like these specific technologies. And I appreciate, David, that you're framing concepts, and even like, and in and as like categories in an archaeological frame, because that to me is like a more interesting way of thinking about structure than this sort of archaeological, like a media archaeological lens, which would frame it almost what feels to me like a meta structuralism. And like, I hope that makes sense, because I think. Yeah, and I think what like another area that does a good job at this is like more like a focus on like infrastructure studies. Like someone like Shannon Mattern, I think, does a good job in sort of the small amounts of things that I've read from her, at sort of not completely adopting like a compression or a contingency framework, but sort of trying to figure out bits and pieces and how they fit or whatever. But okay, but like, I guess my question, or just maybe my point, is that like, it seems like on the side of compression and history, there seems to be this point, and I'm thinking of Galloway and Thacker's book on the exploit, about how like sort of power operates in sort of like, we could even say like not only just periodization of history, but also like these sort of like discrete phase spaces of like biopolitics or something, like sort of with an informatic age, we like enter into a certain definable space of like life and not life, and sort of like politics that emerges from that. And then there's on the other side with someone like Parisi, like there's this huge emphasis on thinking about, and also I'm thinking about Patricia Clough's book on the user unconscious. On the other side, there's like this huge emphasis on like the post biopolitics or after biopolitics, and like the like almost like, let's see, like this sort of like diffusion or like non-connectedness of the way that information is sort of like assembled right now. And I'm wondering if like this position on sort of concepts and categories, and as they're sort of like positioned by these technologies. I'm sort of getting myself lost here, but like like, do you find that your own focus on sort of like categories and concepts as found within these sort of like paradigms that we've been talking about the entire semester, do you think that it's useful to look at them in terms of like biological like biological like how do you say this, like biological sort of like a fixed space of what like biological processes might mean, and sort of like what life might mean, or would you say maybe like it's sort of like opposed to that in a way that would sort of unfix what life might mean? And maybe I'm just asking like what intelligence, particularly now as you see it, is sort of framed as in position to life, and whether you think it's sort of like committed to this sort of changing of what life is, or sort of like fractalizing it, or making it more complex, or sort of like making it more simple. And that's obviously,
I think it's
sort of a long question.
I think it's confusing it, and I mean, whether what ultimately results is considered more simple or more complex, I think is probably something that remains to be seen. But but you know, just as you know, research into epigenetics is making us say, okay, well, you know, the neo-Darwinist synthesis, you know, while quite useful, does leave some things out. I think that, you know, at a certain point, the development of this sort of machine-like intelligence, or the attempt to make a machine-like intelligence, will inevitably have some effect on biology, especially once we get into, you know, into you know, what might be called genuine biotech. That if you can have these sorts of technological machines not operating as large server farms, but actually operating, you know, in bodies, it's, you know, that's an entirely new game. And I think that's one of the realms, and if I didn't mention it, I should have, that is going to be heavily conditioning what applications come next. That, you know, if predictive processing ends up being very useful for, you know, for computers that are injected into the bloodstream or whatever, then that will have such drastic effects on the resulting epistemologies and the resulting ethics, everything, that I think it's impossible to anticipate. So, I mean, I think overall, I would say it's going to be a complexification, simply because you're going to see more overlap, you're going to see more interactions, but there will be so many of them, and they're sufficiently difficult to predict that I don't know. I wouldn't hazard a guess, at least in a couple minutes, of what it might entail. It seems like people are dropping out, so maybe we should Well, and I hear my kids screaming too, so I might call it a day here, but, and just wrap it up.
Excuse me, David, I just have one question. So the papers,
Yeah.
we just emailed them to you, right?
Yep, please email them to me.
Okay.
Some people have gotten extensions, that's fine. If you did not ask me for extension and you have not given me your paper, I guess by the end of today, please email me and tell me when you can get your paper to me.
Okay.
Otherwise, thanks for joining me in this journey. I hope it was as enlightening for you as it was for me. And please email me with any questions or thoughts. And farewell to you.
Thank you, David.
Thanks, and
Thanks,
thanks
David.
Hernan
Thanks,
again
David.
for doing such a wonderful job of administering it and having it go so ridiculously smoothly. Since let me just say, I was worried, so I'm really glad.
Yeah,
it would
please.
be wrong not to be.
Well, on behalf of the new sender, David, I thank you very much. This has been a wonderful intellectual and historical ride. So yeah, I think I speak on behalf of the whole class.
Well, thank you very much, and thanks for thanks for participating, presenting, and I don't know, making me question my own thoughts on these things, since I'm not one of those people who tries to announce things definitively. So I always like getting the opportunities for recontextualization. Best wishes to you all.
Best wishes.
Best wishes.